And joining us is Sally Seidel. She's a physicist and a professor at UNM. So Sally, tell us about this research that you and your team are doing in looking for this elusive particle.
We're members of the ATLAS collaboration at the Large Hadron Collider, which is a large experimental facility in Geneva, Switzerland. And the collider was built to search for new physics, what we call physics beyond the standard model. Anything that's not yet been discovered but might explain one of the fundamental questions that are of interest to the modern scientific community. The Higgs boson is posited as the source of mass of all particles that have mass in the universe.
When you say source of mass, what does that mean?
Mass is the amount of stuff in an object. It's sort of like the weight of the object. How does the Higgs boson give mass to particles? Suppose that I have a particular mass and I jump into a swimming pool. I find that when I'm in the pool, it's much harder to run because of the resistance of the water. The Higgs particle is thought to be a condensate of a Higgs field that fills all of the universe. And that Higgs field interacts with particles to slow them down in the same way that the water of the swimming pool slows me down if I try to run. We think that the Higgs field interacts with particles in the same way. It produces some sort of resistance, effectively, that makes them behave as though they have mass.
Slight differences could make all the difference.
Could make all.
And so maybe that's why we have to build these very intricate and complicated pieces of technology to understand something so small.
That's right. The larger the collider, typically, the higher the energy that it can accelerate the particles with as they orbit in the tunnel. The deeper into the core of a system we want to probe, the more energy we need. So, for example, suppose that I had here a peach, and we wanted to know, is there a pit inside the peach? If I just graze it with my finger lightly, just a little bit of energy, I'll only sense what the surface of the peach is like. And then if I poke it a little harder, I might get my thumb into the peach, but I have to use a lot more energy to poke all the way to the core of the fruit in order to find out if there's a pit. So the more energy that we need, the larger the collider has to be. And we're interested in understanding what's at the very, very core of a fundamental particle.
In effect, the bigger the collider, the more acceleration.
So the reason that we want a high energy proton is because we want, when they collide, for them to completely annihilate the two protons that are colliding, and they are replaced by their equivalent energy. This is the famous equation from Einstein, E equals mc squared, tells us that if we have a certain amount of mass, we can convert it into a certain amount of energy. And what we're doing is we're giving the universe the opportunity, the adequate amount of energy to go ahead and produce whatever particles are possible. And sometimes those are Higgs bosons. Sometimes they're other fundamental particles. The particles in the collider collide every 25 nanoseconds. So if you break a second down into a billion parts, one of those parts is a nanosecond. An enormous amount of information is produced and has to be recorded. So we need an extremely complex and actually physically enormous multi-story device. Some people have called it the world's most complicated camera to capture what's produced in that instant. So that's why these experiments have to be so large and complex, because so much information is produced, and it's produced at such an extremely high rate. The production of a Higgs particle doesn't happen constantly at the Large Hadron Collider. It happens rarely, and so we have to make the conditions for it available billions and billions of times every day in order to capture the few occurrences in which it's actually produced.
Talk to me a little bit about UNM's contribution in this bigger picture.
We use what are called silicon tracking detectors or silicon pixel detectors. These are small silicon devices, not so different from ones that might be inside your watch. Some of the members of my group are involved in designing these, developing them, testing them, traveling to CERN laboratory and building the experiment. We are collaborating with 3,000 people from all over the planet, from dozens of other countries. It's a truly international collaboration.
It just amazes me. It sounds like it takes a village of scientists from everywhere to really, discover something new and cool like this.
Well, it's a very nice opportunity to involve UNM students, undergraduate students as well as graduate students, in actually designing and characterizing devices which will then be used to take this data in this worldwide effort. One of the things that we have to study when we develop the silicon technologies is how well they can withstand the radiation which is naturally produced at the core of the ATLAS detector, right where the collisions occur. So before we install them in ATLAS, we have to understand their response to extensive radiation. And it turns out that Sandia and Los Alamos are excellent places to do controlled exposures of detectors
well, who would have
to
thought that?
So we have developed some
Great.
collaborations with scientists at Sandia and Los Alamos, and this gives our students an opportunity to do experimental studies right here in New Mexico, not only in our laboratory, but also in collaboration up at the labs.
So tell us, if you will, what's it like on a daily basis communicating with CERN?
We're in near constant communication with our colleagues at CERN via the internet. We have audio and video meetings almost around the clock. Rui, we've got your graph up here of the B sub C with the L2 star B trigger. Could you please tell us a little bit about your results from this week? The collaboration includes institutes that span the globe. We need to be able to wake up in the middle of the night and connect to a meeting to talk about science.
Is this meant to be long-term? When can we actually expect to see something with the Higgs boson?
So we began designing this experiment in 1995.
Okay.
The experiment began to take data in 2009. The data that were actually used for the discovery of this Higgs-like particle were taken in 2010 through 2012. So now we have an indication that this particle exists, but to check whether it is actually the particle predicted by the Higgs model requires understanding many of its properties.
Okay.
And hundreds and thousands of people right now are actually studying the data in order to understand whether it has the so-called spin or mass properties that one would expect. The collider will continue to run through this coming February 2013, and then it will shut down for some short period of time, about a year, and after that it will come back online at a higher energy and with a higher rate of collisions so that we can take the data even more efficiently. We're searching for many processes that are so-called beyond the standard model.
With this collider?
With the same collider.
Not just the Higgs boson.
That's right, that's right. So the Higgs boson is very interesting, and I'm really excited to have been, in some way, a small way, a part of it. But that's not all there is. And so the collider will continue to take data perhaps for another 10 or 20 years, and we hope to have many more discoveries. Some of them might be even more interesting than Higgs.
What do you think the future holds now?
Some people feel that perhaps this particle that has been discovered opens the door to new questions that are beyond the standard model. Perhaps the precise mass of this particle is actually inconsistent with our understanding of the standard model, and maybe we will need to revisit the whole model. And there are other questions that physicists are are already very interested in. For example, there's the question of the so-called matter-antimatter asymmetry in the universe. The question of why is there only matter? Our bodies are made of matter. Everything around us is made of matter. There appears to be almost no antimatter in the universe. The fundamental laws of physics, quantum field theory, predict that there should be an equal amount of matter and antimatter. When we collide the particles at the Large Hadron Collider, an equal amount of matter and antimatter are produced.
Interesting.
So one would think that at the dawn of this universe, at the Big Bang, there must have been an equal amount of matter and antimatter, and all of the antimatter seems to have disappeared. Where did it go? It's a big puzzle. Why is there the so-called asymmetry? We're actually interested in studying systems that are bound states of heavy quarks. Those can be used to understand the strong force. There are 4 fundamental forces in nature, and the strong force is the force that binds the nucleus together. It holds the protons and the neutrons in the nucleus. Heavy quarks are interesting because they don't appear in our daily life. What we find in our daily life, what our bodies are made of, what our houses are made of, are protons and neutrons, which are made of light quarks. The heavy quarks we only find in particle collider experiments or in cosmic rays. They very rarely manifest themselves in daily life, but it turns out that they may actually hold the keys to the answer of the question, why is there matter but no antimatter present in our universe today?
Well, thank you so much, Sally, for joining us. Really interesting stuff that you're involved in with your students.
Thank you.